1B. Why is accuracy important? If you want this is like the layup question. So if you want to like show your awesomeness and answer a question, but you want it to be really easy, here you go. Why is accuracy important? Why do we need accurate watches when we do the Olympics? There you go. Right? Why is accuracy important? Because we need to get the right answer. You need to get the right answer. If you don't have accuracy, then there's no point in doing the races, right? If you cannot measure the times accurately, why even do it? There's no reason to do it because no one would believe it. You'd get to the end and it'd say, lady number 3 won, and everyone would be like, well, yeah, but this clock's not accurate, so who knows? You would have to do really long races that were almost guaranteed not to have photo finishes so that it was obvious who won, which obviously doesn't make sense for things like the 100-meter dash if Usain Bolt's not in it. So those are kind of things to think about. So you have to get the right answer. That's why that one matters. Precision's a little trickier. Why do we think precision matters? Gavin, what do you think? Why do you think precision matters? Yes, because your numbers need to be consistent. Because if, let's say that I'm measuring 2 different races, so I'm doing like 3 semifinals or whatever, okay? If I'm not precise, then how do I know that the numbers for race 1 are similar to the numbers in race 2? If that's true, then it could be that people in race 2 have an advantage because their times are faster, even though they shouldn't be faster. So the reason why it's important for precision in measuring is numbers must remain consistent. When you're doing lab measurements, if your measurements aren't precise, you could get the right answer, but for the wrong reason. Okay? And if your numbers aren't precise, it makes it hard to know how good your data actually is. So that's why precision isn't important. So examples from the video. Let's see. Zoe, what's an example for the video? You can pick accuracy or precision, whichever one you want.
For precision, the clock.
Yep, how do they work as an example? You're right.
It showed that they're the same, one of them was 1 second off every time.
Yeah, clocks are similar in measurements. I guess I should say clocks are always similar. They're always similar in their measurements. So that, the thing you should know is you're never going to be completely accurate. You can be really close, but you're never getting completely accurate. So precision means that even though I'm not perfectly accurate, I'm getting consistent numbers every time. So it's not like one time I'm 0.01 seconds off, and then I'm 0.07 seconds off, and then I'm 0.1 seconds off, and then I'm 0.1 again. They need to be similar values every time. Good. Okay, and let's see. Justin, what about accuracy? What's an example that they had for accuracy? Yeah. Yeah. So like the times, you're talking about like on the image of them crossing or whatever. So times on crossing for photo finishes. Yeah. If you have a photo finish, you have to trust that your timer is correct. Okay? Because otherwise you can't guarantee that you know who the winner is. That's why years ago, Okay? Years ago in the Olympics in like the 70s and 80s, you frequently had ties because they couldn't measure their clocks accurate enough. So if they only went, so like stopwatches go to like 1/10 of a second. Okay? Well, 1/10 of a second is a pretty big gap. So you could have two people finish not at the same time, but in 1/10 of a second, it's the same 1/10 of a second. So now we're able to be more accurate, so you can get more delineation between people, especially on these kind of faster track and field races and that sort of thing. And it's true for any kind of measurement in the Olympics. So even if you're talking about how far did the discus go, right? They don't do it anymore. They don't get out like a little trundle wheel and they don't measure out to where it is. They use lasers to figure out how far from the beginning they are and that sort of thing. So you have to trust that those things are correct. All right, any questions up to here? Nice. All right, number 3. So how do we quantify how accurate something is? So in other words, how do I know if I'm accurate? We do something called percent error. Okay, percent error. Here's how you do it. Your percent error equals your measured value minus your expected value divided by your expected value times 100. So, how do I figure out if I'm accurate? I take the number I measured on my clock, I subtract it from the measurement I should get, and then I divide it by the number I should get, and then I multiply by 100. Okay, so I get a number. Great, Mr. B. What does that number actually mean? So, if your percent error is less than 10, you're accurate. You're very accurate. If your percent error is between 10 and 20, you're accurate. If the percent error is greater than 20, you're inaccurate. So, when you do a calculation, if you get a percent error that is smaller than 20%, you're good. You're fine. Everything's gravy. If you get a percent error that's more than 20%, then something's wrong. And there's lots of reasons it could be wrong. It could be that you did your measurements wrong. It could be that the lab is hard and the numbers just don't come out very well. There's a lot of different things it could be. But that is how you figure out percent error. So let's do a little bit of an example here that might help you, and we'll see if this will kind of help kind of solidify this for you. So there's 4 possibilities. You could be accurate and precise. You could be accurate but not precise. You could be precise but not accurate, and you could be neither. So let's start with both. So accurate and precise. If you're accurate and precise, not only do you get what you want, but you get the same thing every time. So you hit, it's kind of hard to see on here, but you hit the bullseye every single time. That would be accurate and precise. If it's neither, not only are your arrows not consistent, but they're all over the place, okay? So I hit here, then I hit here, then I hit here, then I hit this place, then I hit down here. I'm all over the place. If I'm precise but not accurate, I hit the same spot, but it's not where I want to be. And then lastly, If I'm accurate but not precise, this one's the weird one. My average is correct, but my numbers are not consistent. If I averaged that, I would hit the bullseye. But I think you all agree that's not what it's supposed, right? Like, okay, yes, the average is the middle, but you never actually hit the middle. So that's not really, it's not really what we want. This is what it needs to be. You need to be accurate and precise. So we talked about how to figure out accuracy. How do you figure out precision? The way you figure out precision, so this was accuracy. Let me do precision here in a different color. The way you figure out precision is, are your trial measurements consistent? So think about the lab you guys just did. Were the numbers you got for all three of your trials the same? Right? So some of you found that when you did your bounce heights, you got 21, 22, 21 again. That would be precise. Accurate is, how high should it have bounced? Okay? So precise is, how consistent are your measurements to each other? Accuracy is, how close do you get what you should get? There's a way to do this with graphs also. So I'll show you this also here. So when I look at my graph, because on the lab you guys did, you don't have a way to calculate accuracy. We don't know what it should be. So how can I figure out accuracy and precision just by looking at the graph? So the way you can figure out precision on a graph is, how close are your dots to, like, how straight of a line do your dots make? So mine make a fairly straight line. Okay? So I can say that, okay, that number might be accurate. It might be precise. They get kind of, they're kind of close to each other. That's my precision. Accuracy is, how close are they to the line? Well, none of mine are all that close to the line, so that makes me worry that maybe this isn't all that accurate. But here's another really good one to look at. All right. If I dropped my ball from a height of 0, what should its bounce be? 0. Look at this blue one. If I dropped mine from a height of 0, according to my graph, the bounce height would be like negative 20 centimeters. That's not great. That's not that good. So am I accurate on this? I'm probably not. Just by looking at my graph, I'm probably not all that accurate. Which makes sense. I literally made those numbers up. Probably not going to be very accurate if I just make the numbers up. Okay? Which is a nice word of warning to you. Don't make numbers up in labs, because I can usually tell. So make sure that you're working your way through them. If you have trouble, we can always work through it and figure it out. Make sure you're doing that. So that's just a little bit on how you can do accuracy and precision, both by looking at the numbers and doing some calculations, but also just by looking at the data visually on a graph. How close are you to your fit line? You should be very close to that if you're going to be accurate. They should also be along the lines of each other if they're precise. That'll help you with that too. And you should probably go through 0 on most of these. Not all of them, but on many of them. Okay.